do you read?
Land clear, and we're doing Mach 10.3 at 180 AS. Okay, it looks to me like the yellow overdue is Mama.
Columbia, you got perfect energy, perfect ground track.
Roger that.
Live television precision picture from the long-range optics at Dryden.
Columbia, you're coming right down the track. The tracking data, nav data, and pre-plan trajectory are all one line on our plot board here.
Roger, we can cut.
This TV from the chase plane. Ready to start the big sweeping turn into the runway.
Cruise has a tally.
Trip, altimeter 3009er.
Roger that.
And turning on the final, your winds on the surface are calm. Put on glide slope. Approaching center line, looking great.
A pilot's ultimate challenge. Landing a 100-ton shuttle following a week in space.
5, 4, 3, 2, 1, touchdown.
Landing on the numbers. Landing with no go-around.
Beautiful, beautiful.
Let's take it up to higher, Joe.
Gonna dust it off first.
The whole state is all electric fire machine. Okay, super.
Okay, convoy's on its way.
Convoy on. Wheel stop on the Columbia. Wheel stop.
The Textron Lycoming Williamsport Division proudly presents On Landings, a program dedicated to making aviation safety record even better. As you know, being a safe pilot means combining your working knowledge of aviation with current skills and experience, tempered by good judgment. Landing phase accidents are responsible for nearly half of all general aviation statistics. By fortifying your knowledge of the whys and wherefores of approach and landing accidents, this program can make you a safer pilot. In the first part of this program, Part 1 will deal with undershooting and cross-control stalls, the kinds of accidents that can happen before you reach the runway. And we'll also talk about hard landings, porpoising or pilot-induced oscillation, and loss of directional control, problems that you encounter after reaching the runway. Part 2 explores problems stemming from improper braking, landing long, and along with that, poorly executed go-arounds. And Part 3 addresses the topics of gear-up landings, landing gear emergencies, landings in inclement weather, landing at night, and human factors. We believe On Landings to be the most comprehensive educational safety program on this subject ever assembled. Much of the material for this program came from actual case histories taken from the files of the National Transportation Safety Board and NASA's Aviation Safety Reporting System. Files which were painstakingly merged into a comprehensive dissertation on landing phase accidents and how they can be avoided. On Landings is not a substitute for basic pilot training. Although this program can be seen in one sitting, we strongly recommend that because of its length and the detailed and diverse nature of its contents, the 3 parts be viewed separately. And with that out of the way, let's roll up our sleeves and get started. We're going to begin this program by discussing 2 classic killers. By that I mean 2 kinds of accidents that often result in serious injuries and fatalities. I'm talking about the undershoot and the cross-control stall. At one time or another, every one of us has miscalculated an approach and started to undershoot the runway. It's hard to forget that sinking feeling you had when you first realized that the airplane might not make the runway. Poor pattern or circuit technique is one of the frequent causes of undershooting, and a sure way to wind up in the boonies is not to pay attention to how far out you've flown on downwind. It also doesn't really matter much whether you got out there all by yourself or were forced there by other traffic. Either way, the fact remains that you're out there where statistics show you're at risk. Too wide a downwind leg can also contribute to undershooting. If you're on downwind and your passenger says, "Hey, is that an airport over there?" maybe you're out too far. Another contributing factor to the undershoot is not maintaining adequate power on final. Some pilots get a thing called runway fixation and unconsciously try to carry the airplane up to the landing spot by easing the nose up without adding power. This doesn't work very well. As a matter of fact, instructors standing by the runway watching their first solo students pull this stunt have been known to stand on their toes, shouting incantations in order to get the student and the airplane at least to the numbers, a process of dubious aerodynamic value, even though it does seem to help the instructors. Another cause of undershooting is something called poor configuration management, which of course deals with the untimely application of flaps, gear, and so forth. For example, the pilot who decides to apply full flaps early in the approach without compensating with power might find himself running out of airspeed, altitude, and inspiration all at the same time. So you see, by not setting yourself up properly, you can set yourself up to undershoot the runway and ruin your whole day. All right, now that we've seen some of the don'ts, let's start talking about some of the do's. When traffic isn't a factor, a good rule of thumb is to turn base when the point of intended touchdown is 45 degrees behind the wing. This technique provides a consistent viewing perspective for every pattern. And remember to anticipate that 45-degree point, particularly when a significant tailwind exists. At the airport where you're based, your normal tendency might be to use a crutch, such as a familiar ground reference, to turn from downwind to base. But don't forget, Farmer Brown's barn isn't going to be at an unfamiliar airport. So practice using the 45-degree technique. It's a good habit. When you're in a pattern with other airplanes that are flying at comparable approach speeds, you can avoid flying an extended downwind by starting your turn to base just after the airplane you're following turns final and passes behind your wing. By the way, it's a good idea to have your landing lights on when you're in the pattern, particularly during times of reduced visibility. Experienced pilots often use a series of imaginary windows on approach. These reference points in the sky are great aids in determining whether or not the approach is within the desired vertical and horizontal limits. The first window should be encountered immediately after turning final. If the approach is not within the limits of the window, the pilot can either correct the approach or execute a missed approach. The key to making that first window work for you is to roll wings level just before you fly through it. By the way, if there are obstacles between the windows and the runway, we think it's a swell idea to either raise the window or move it. The last and most important window is the one at the threshold. You should be at the required airspeed and height to begin your flare when passing through this one. If you've timed everything out just right, you should be able to roll wings level on final right on the extended runway center line and fly through the windows to the runway. Flying through the windows is an excellent aid to flying a stabilized approach, though, which is our next topic of discussion. But before we get into talking about flying a stabilized approach, it's important that we talk for a minute about flying the right airspeeds. Pilots of large aircraft always determine what their approach speeds will be for downwind, base, final, and short final before initiating their approach. To find them, all they have to do is calculate the aircraft's landing weight, then look in their charts for the appropriate reference airspeed. That's the airspeed known as VREF. VREF is a keystone, or basic building block, for every approach. VREF is a value which is usually different on every approach, but it's always derived from the airplane's stall speed at its estimated landing weight. To VREF, the pilot adds the additional airspeed required to maintain an adequate safety margin while banking and maneuvering in the pattern, as well as additional airspeed to compensate for wind gusts, turbulence, and wind shear. Approach segment airspeeds, which are based on VREF, are vital tools in making sure that the airplane doesn't have an extra margin above the stall speed for maneuvering and turbulence, but has the right extra margin. Professional pilots don't want any more speed than they need, and they certainly don't want to have any less. In comparison with large transport category aircraft, smaller aircraft don't usually come equipped with VREF tables, or for that matter, with tables that give recommended approach segment airspeeds at different landing weights. But such tables can be developed, and we urge you to prepare and use your own. We have provided a sample table in the handout that accompanies this program. Before you begin to fill it out, though, we want you to be sure to hear what we have to say about VS0 in Part 2. Incidentally, since most pilots refer to VS0 as VSO, we'll do the same. Here are some rules of thumb for determining approach segment airspeeds. When you're on downwind, we recommend that you fly at an airspeed that is no higher than the top of the flap operating range and, in no case, lower than 1.4 VSO. Continue to maintain no less than 1.4 VSO until after you've turned on base, and hold 1.4 VSO until after you've turned final. Then let your airspeed decay to 1.3 VSO as you near the runway. That's what we call short final, but make sure that all your maneuvering is behind you first. Of course, if you're encountering any turbulence, wind gusts, or wind shear, you should compensate for them with additional airspeed on each segment of the approach. We'll discuss the effects of turbulence and wind gusts in greater detail a little later on. Right now, however, let's talk ourselves through a stabilized VFR approach. First, of course, you make a normal entry to the traffic pattern or circuit. Then extend your gear on downwind. That is, if it's not already bolted in place, like it is on a Stearman. And when you're abeam your point of intended landing, reduce your power to the predetermined value that works best for your airplane. And while holding your altitude with pitch, slow yourself down in preparation for turning base. Then set partial flaps, if you haven't already done so, and if you've reduced your power properly, you can now trim the aircraft and set up your descent. Begin your turn to base at the 45-degree point, traffic permitting, remembering to keep your angle of bank to 30 degrees or less on this turn, and 30 degrees or less when you turn from base to final. Also, keep the ground track as rectangular as possible. Should you need to increase your rate of descent, you can do so by further extending flaps to increase drag. If you do, remember that you've just modified your approach configuration and that you may have to add more power to stay on glide path at your targeted airspeed. Now, a fundamental key to flying a stabilized approach is understanding the importance of the interrelationship between pitch and power. At any targeted airspeed, in any configuration, applying more power will make the glide path shallower, and reducing power will make it steeper. The fact is that pitch and power are so interrelated that changes in one must be compensated for by adjustments in the other. So after a glide path has been selected, the means of staying on it and maintaining your targeted airspeed can only be achieved by adjusting pitch and power together to compensate for variables such as wind and drag. Experienced pilots know the power settings and airspeeds for different landing weights, drag configurations, and principal rates of descent. If they don't know these numbers, they'll have them written down for easy reference, or know where to look them up, and can quickly and efficiently select the normal power setting for each segment of the approach for a no-wind condition. Then, when flying the actual approach, they only need to make minor pitch and power adjustments to maintain the selected glide path and airspeed. And with experience in type, the use of power becomes automatic. The important point to remember is to never let your airspeed decay below the targeted speed for each segment of the approach, and never let the airplane sink below the selected glide path. If you do get too low, add power. But never allow yourself to get behind the power curve. Oh yes, I'd also like to remind you that full flaps should be used on all normal landings. Remembering, however, that once flaps have been extended, they should not be retracted. Which is why it's a good policy not to go to full flaps until your landing is assured. Now let's talk about flying a stabilized IFR approach. You'll find that the same basic concepts and techniques we've been talking about apply. As you approach the airport, the first thing you want to do is transition the airplane to an approach configuration. That is, you want to slow the airplane to a lower airspeed and retrim it while maintaining the assigned altitude and heading. To do this, first slow down to your initial approach airspeed well before you intercept your descent glide slope. That is, of course, unless ATC requests otherwise. Some pilots extend their landing gear to help them slow down, then add flaps after the airspeed has dropped into the flap operating range, remembering to retrim as necessary. Now, when you intercept the glide slope or reach the final approach fix, put your gear down if it's not already down. An additional power adjustment may be necessary at this point. You should now be able to hold the selected airspeed and set up a stabilized rate of descent with few, if any, additional changes in power. For most light airplanes, when the runway's in sight and the landing's assured, extend full flaps, but make sure you're on top of the airplane, because if you add flaps too rapidly here and don't properly compensate with pitch and trim, you could balloon right back into the clouds. But on the other hand, a properly executed, stabilized approach will set you up for a good landing. You might be interested to know, by the way, that accidents involving undershooting the runway are usually much more serious than overshooting or landing long. If you've never stopped to think about it before, it's because impact velocity, momentum, and kinetic energy are all much greater in an undershoot than when you roll off the end of the runway in an overshoot. So, if you ever have any doubt about making the runway, either carry or add enough power to assure yourself a safe landing. And as always, on any approach, be absolutely sure that power will be available when you need it. Don't forget any critical engine-related item. Use your checklist. If you think this sounds trite or basic, it's forgetting the basics that can kill. A significant number of all landing phase accidents are caused by loss of power. And they're usually related to some basic step the pilot simply forgot to do, like not adjusting the mixture for density altitude, selecting the wrong fuel tank, or not using carb heat. And let me re-emphasize this point one more time. Whether you're VFR or IFR, never descend below your approach path or allow yourself to get under the targeted airspeed. If you do, adjust power and pitch immediately. And anticipate the need, okay? I mean, look at this. See what's wrong here? Now look at this. Well, at least it's better. And finally, in most undershoot accidents, the pilot is unconsciously trying to hold altitude or make the runway through the use of elevator alone. Please don't do this. You see, if you keep coming back on that elevator without adding power, you could bleed off so much airspeed that you'll get behind the power curve and mush or stall into the ground. A perfect way to sucker yourself into the ground is to shoot a long, low approach, especially in unstable air when there's a high density altitude because you can wind up behind the power curve even though the throttle's wide open and you're generating all the power the engine can muster. If you find yourself in a situation like that, the only thing you can do is lower the nose and regain airspeed, if you've got the altitude to do it. We simply cannot overemphasize the importance of using the proper combination of pitch and power throughout the landing approach. Now, let's take a look at some of the key points so far. Know and use the appropriate approach speeds. Never get below your targeted speed. Fly the proper glide path. Add power anytime you even think you're too low or slow. And remember that pitch and power are interrelated. We've been talking about undershooting, and now I want to show you a wonderful landing aid, one that'll really help you with your approaches. I'm talking, of course, about the aim point, something we've all heard about, but seldom really gotten around to using. An aim point is your imaginary bullseye on the runway. It can be between two runway lights or whatever's convenient. It's the reference point at the end of your selected glide path. It is not the actual point of touchdown. Now, if your aim point appears to be moving toward you as you fly down your glide path, you'll know that your airplane will overshoot that point and that you must reduce power. If your aim point remains constant, you know you're on the glide path you've selected. But if the aim point appears to be moving away from you, you can be sure that you will undershoot the point, even though you are maintaining your targeted airspeed. What you have to do then is add power and adjust pitch so you can maintain your airspeed while you reacquire your glide path. Then continue your approach. Also remember to flag that aim point on the runway with a corresponding spot off to the side, which you can use for reference if your nose blocks your forward view. Once you've selected your aim point, you must also select the right glide path. If you're not using a system such as VASI or ILS, glide path selection becomes a personal decision. Select the glide path that works best for you, but make sure that the glide path you choose allows for clearance of all obstacles and for a safe rate of descent. Looks okay. Are you sure? Here is a pilot's eye view of a well-selected glide path. This one, on the other hand, is too high. And this one is too low. And this one is definitely too low. A visual approach slope indicator, or VASI, is often a good aid in helping you establish the proper glide path. Here is an example of a standard VASI system. A word of advice, though. All VASIs will keep you clear of obstacles, but glide angles may vary from VASI to VASI. Some complex standard VASI systems also provide multiple glide angles to assist everything up to and including jumbo jets. On the other hand, many small airports in the U.S. have various kinds of non-standard VASI systems. One popular low-cost system consists of 3 panels, sometimes built of plywood and occasionally built of plastic. Some non-standard VASIs are painted black. Some are painted white. Some are also painted black and white. Some others are painted fluorescent orange. And some are not painted at all. Some non-standard VASIs are day use only, and some are lighted for nighttime use. You can always tell the day use only because you can't see them at night. All VASI systems, both standard as well as non-standard, will guide you to a predetermined aim point. But you have to be careful in flying a non-standard VASI because that predetermined aim point may be suckering you into landing long. Why, you ask? because you flew to the aim point that the non-standard VASI directed you to, rather than one that was appropriate for your aircraft. We'll discuss this in greater detail in Part 2. In the States, the Airman's Information Manual provides a detailed description of how standard as well as non-standard VASIs work, while the Airport Facility Directory, or AFD, provides VASI glide angle information for standard VASIs only, and on a runway-by-runway basis. In Canada, the comparable reference publications are the AIP Canada, also known as the Aeronautical Information Publication Canada, and the Canada Flight Supplement. There is another way to establish your glide path, of course, and that's to fly the glide slope portion of the ILS or MLS if either is available. Regardless of how you fly your aim point, though, have a plan. Don't just wing it. Statistics show that it's in winging it that pilots get into real trouble. So be careful. Now, so far we've talked about undershooting problems generated by the pilot. Problems such as not flying a good pattern, poor power and pitch management, and so forth. Now let's talk about undershooting caused by wind and turbulence. On final approach, your glide path can be affected by wind, wind shear, microbursts, and other atmospheric turbulence, as well as by wake turbulence. Wind shear is a sudden, drastic shift in wind speed and/or direction in a vertical or horizontal plane. This may occur at any altitude. It is a serious factor for large aircraft operations, but can be a hazard for small aircraft as well. Microbursts, on the other hand, are sharp, very strong downdrafts associated with thunderstorms. They can be impossible to outmaneuver, and since they are completely invisible, are a very good reason to stay clear of any airport that has a thunderstorm in progress. Another good reason to steer clear of airports in the vicinity of thunderstorms is because of the increased risk of radical shifts in wind direction and speed. A headwind on final may suddenly turn into a tailwind and cause a sudden high rate of descent. Don't forget, however, that turbulence can be generated by other things as well, such as strong air currents spilling across nearby mountains, winds gusting over wooded areas that parallel runways, and turbulence generated by wind blowing past hangars and other structures. So always expect the unexpected, and when you encounter it, especially on short final, be ready to add power and go around. A good rule to live by: the sooner you add power, the less likely you'll be to wind up between a rock and a hard place. Remember, it's considered a below-average landing if you have to taxi the last 100 yards or more to the runway. And finally, whenever you operate in the vicinity of an airport served by large aircraft, be alert for wake turbulence. If you do operate in or out of a large airport, study the wake turbulence avoidance procedures from time to time. They're published in the Airman's Information Manual, the AIP Canada, and other publications. And that just about does it for undershooting the runway. As we mentioned at the beginning of this part, however, stalls are another frequent cause of landing phase accidents, and the deadliest of all of these is the cross-control stall. A cross-control stall is usually set up on base, and the potential for it becomes greater in the presence of a tailwind, which of course results in a higher ground speed on base, and thus less time to properly set up your turn to final. Now, add to your tailwind a little something that diverts your attention, such as conflicting traffic, and the fact that your passenger is a little old lady who can't handle steep turns, and the scenario is complete. Between the tailwind and the traffic, it's very easy to get behind your airplane and overshoot your turn to final. You don't want to make a steep turn because of your passenger, but you also want to avoid the embarrassment of overshooting your turn to final, so now you've got to do something radical. Why would you be embarrassed? Well, when you took off, every pilot you knew was milling around the airport just looking for something to talk about. And you know for a fact that they're all down there right now watching your every move. So you know you've got to be real cool. As you realize that your airplane has flown past the extended runway center line, 3 choices come to your mind. Choice number 1, you can go around and try again. But if you take it around, you just know that all those macho pilots down there are never going to let you forget it. You just know it, don't you? Choice number 2, you can steepen the bank. A lot. Sort of like fighter pilots do in the movies and roll out right on the center line. That's what the peanut gallery would like to see you do. But that would make your passenger tense up. Besides, you know that your stall speed will increase significantly with your angle of bank. You've known about the stall speed curve since you started flying, and you know that below 30 degrees of bank, you have a good safety margin. But above that, the stall speed multiplier increases a lot. You also know that you don't have the airspeed to make that steep turn right now, because in this example, your airplane has a wings level stall speed of 51 knots, and you've already slowed to the final approach speed of 66 knots. But in a 60-degree turn, you'll stall at 72 knots. And 72 knots is 6 knots faster than you're going right now. So forget number 2. Now, the only other choice you can think of is choice number 3. And that is to increase the rate of turn, but keep the bank angle shallow by using inside. In this instance, left rudder and opposite aileron. This results in a skidding turn with inside rudder and enough opposite aileron to let you keep the bank angle nice and shallow. Of course, you'll need more up elevator now, because the combination of inside rudder and the drag of that down aileron makes the nose tend to drop. But as you add more up elevator, you're slowing the airplane, and you're approaching a cross-control stall. That left wing, the one with the aileron down, is about to reach its critical angle of attack. And when it does, it'll stall and snap roll you sharply to the left. And there you'll be, in the middle of an air show, literally shooting your final approach. As a matter of fact, it's a good thing that little voice told you to go around, because with an approach like this, no one, not the pilots watching you from the ground, not even your passenger, would ever speak to you again. You know what? All of a sudden, choice number 1, going around, didn't look so bad after all, did it? You see, you've already made 2 mistakes. Overshooting your turn from base to final was the first one, but not flying the appropriate airspeed for your base leg was your second mistake. You had slowed your airplane down too soon. You were already at 1.3 VSO, and that's the short final approach speed, and you were still on base. I think by now you're beginning to realize that safe landings begin with pre-planning and must be executed with precision. So, now that I have your attention, let me give you some pointers. Complete as much of your before landing checklist as you can before entering the pattern. It will help you avoid a work overload situation and let you be more responsive to changing conditions. Look outside the cockpit. Look around. Check those classic wind indicators. Flags. Ponds. Smoke, and so forth. Listen to your radio. If there's a Unicom in operation or a nearby ATIS, get wind speed and direction. And when there's a direct crosswind and you have the option, set up your pattern so that you'll have a headwind on base rather than a tailwind. Remember these key points. Airspeed control is vital. Never get below your selected approach speeds. Watch your angle of bank and keep your turns coordinated. You know, old pilots don't always agree on everything, but one thing they'll all tell you, and that's that a bad approach is a setup for a bad landing. So if things don't look right or don't even feel right, take it around and try again. We'll have more on go-arounds in Part 2. Now we're going to look at 3 types of landing accidents: the hard landing, the bounced landing, also known as pilot-induced oscillation, and loss of directional control on rollout. These accidents are usually not the killer-type accidents like the cross-control stall and the undershoot, but can still result in substantial aircraft damage, many injuries, and a whole lot of pilot embarrassment. Let's begin by talking about hard landings. Did you know that drop-in type accidents, or hard landings, cause a great deal of monetary damage to airplanes every year? Hard landings take their toll in deaths and injuries, too. These accidents result from several causes. You can set yourself up for a hard landing by not looking out ahead of the airplane and losing your perspective relative to the ground. Loss of perspective can also be the result of improper scanning during flare and touchdown. Remember to look outside the cockpit, way outside. And don't forget to use your peripheral vision as well. It's something you learned way back in pre-solo, to focus your attention ahead of the airplane. And by the way, trying to focus ahead while landing into the sun with your windshield dirty doesn't help either. Cleaning it up should have been part of your pre-flight. Hard landings are also the result of distractions. One typical distraction is the passenger in the right seat who won't keep his mouth shut. Have you ever been on a short final and suddenly hear, "Hey, what's all that smoke over there?" Don't be distracted. You see, the landing is the last part of the flight, the part where you're the most tired, and yet it's the place where the most concentration is needed. To help alleviate distractions during final approach, many airlines have adopted the sterile cockpit rule. That is, that below a certain altitude, all conversations are limited only to matters concerning aircraft operations. It's a rule you may want to adopt for your own airline. We've also found that wearing headphones during flight can help discourage conversations with your passengers. Now, let's talk about ballooning. Ballooning is another cause of hard landings. Ballooning is often the result of excess airspeed combined with poor flare technique. Yanking back on the controls just before touchdown can put you several stories above the runway with your nose pointing up and your airspeed rapidly going down. And if you don't correct the situation quickly, you may have to pay the piper, or at least pay for the piper, or Cessna or Beech. With the nose already pitched up, some pilots will also make the mistake of adding an excess burst of power in a balloon situation, which can only add insult to injury and can result in a drop-in of monumental proportions. Should you find yourself in a ballooning situation, ease the nose over. Never shove the nose down, and add power if necessary. On the other hand, if your sink rate is high after you balloon, adding power is the only solution. You may still land hard, but usually with little or no damage. Also remember, however, that the decision to add full power and go around may be the best way for you to avoid a hard landing in this situation. Another cause of a drop-in or hard landing is undershooting the runway and then trying to stretch the approach without adding power. As you recall from our discussion earlier, you may make it to the threshold, with luck, but might not make it to your intended point of touchdown. And we're not talking about floating in ground effect here either. No, sir, we're talking about being up to 50 feet above the runway and out of airspeed and inspiration all at the same time. With that kind of altitude remaining, if you run out of airspeed and you stall, you're going to crash. Also beware of running out of elevator control during flare. A typical example happens when you're coming in too slow with too much weight up front. When you try to flare under these conditions, you find out, rather abruptly, that you might not be able to. A high rate of descent can make matters even worse. In situations like this, you simply can't rotate from your approach attitude into your landing attitude in time. The problem can be avoided easily enough, though. All you have to do is calculate your CG beforehand and avoid a forward CG by shifting passengers or cargo aft, or even adding ballast. Oh, and don't forget that you can also wind up with a forward CG when you're lightly loaded, something you probably haven't thought about lately. Summed up, if you think you're headed for a hard landing, add power to arrest the sink rate. Keep your wings level. And if you decide to go around, make the decision sooner rather than later. And most importantly, always fly the airplane. Now, let's move on to a new subject, the bounced landing, or pilot-induced oscillation, also known as porpoising. With the introduction of tricycle gear, the problem of bounced landings was supposed to become a thing of the past. Not so. Innovative pilots seem to keep discovering new ways of messing up what should be routine. And the bounced landing is a classic example. In a bounced landing, the airplane comes in nose wheel first, setting off a series of motions that not so gracefully imitates the action of the porpoise, hence the name. The problem is one of improper aircraft attitude at touchdown. It may be caused by distractions, or by inattention, by not knowing where the ground is, or having too simplistic an approach to flying and neglecting things like trimming elevator control forces before landing, or trying to force the airplane onto the runway. No matter what the cause, the situation must be corrected, and it must be corrected immediately. Some pilots try yelling at their airplanes as they porpoise down the runway. We found, however, that this usually doesn't help much. What would help was proper trimming in the first place. As a matter of fact, we found that improperly trimming the airplane is probably the biggest single contributor to the whole bounced landing problem. What happens is that, in ground effect, the elevator or stabilator is less effective than it is at altitude. And since most airplanes are also more stable longitudinally in ground effect, the nose feels heavier and requires more effort to hold off during flare. When no trim is used, the nose feels so heavy that you want to relax back pressure as soon as the airplane lands. And when you do, you're right back up in the air. Again, and again, and again. By the way, ground effect, which is really a reduction in induced drag, is a factor from the surface to a height above the ground that's the equivalent of about one wingspan, which is 40 feet for most light aircraft. And it doesn't matter much whether you're a transport or a four-seater. P.S. Don't try to figure this out now, but this nifty chart is in your handout and can tell you more than you ever wanted to know about ground effect, which, as we mentioned earlier, is really a reduction in induced drag. Okay, let's move on. We've all been taught to maintain the proper pitch attitude during flare, haven't we? But unfortunately, many of us never got the chance to understand what it really meant. So, what is a proper pitch attitude anyway? Well, for tricycle gear aircraft, both large and small, it's the landing attitude that lets you keep the nose gear off the ground until after the mains have touched down. For a light single, this is what it looks like from the cockpit. This is the view from a light twin. And from a bizjet. Do you see any difference? And although we couldn't afford the cockpit view, from the Concorde. The fact is that you'll need to develop a feeling for your specific aircraft. And the best way to do this is to stay proficient. You need to know what it feels like for different weight and CG combinations too. And you need to know what it looks like, both the view and the sensation. They're important feelings, and they simply cannot be quantified. Now then, bouncing or porpoising can also be caused by improper airspeed control, and that begins with an approach that is usually too fast. As a result, the airplane floats merrily down the runway until the pilot consciously, or unconsciously, tries to force it on, a phony grease job, even though it's still at flying speed. What can happen then is that a gust of wind, a bump in the runway, or even a slight jerk on the wheel or stick will put it right back up in the air again. If this happens to you, re-land the plane, making sure this time that the nose is in the proper pitch attitude when it touches back down. Whatever you do, don't push the nose over. Instead, add back pressure smoothly and continuously throughout the flare. Trimming is necessary to help dissipate your airspeed. Hold it off. Hold it off. Hold it off and... Ah, that sounds better. In a porpoise situation, the pilot gets out of sync with the airplane because he's either holding too much back pressure when he shouldn't be, or not holding enough when he should be. At this point, he becomes the victim of his own erratic control movements. To add or not to add power? Well, that depends entirely upon the situation at hand. However, should you make the decision to go around, add full power and do it. Remember, too many airplanes have been pranged on landing because of the pilot's fixation about getting the airplane on the ground. Now, let's review. To avoid porpoising on landing, always trim your airplane for a stabilized approach. Avoid excess floating. Use the appropriate approach and landing speeds. Don't be distracted. Maintain a proper pitch attitude during flare. And keep proficient. Let's move on. The next subject is loss of directional control, something else that tricycle-geared airplanes were supposed to do for us. Engineers thought that tricycle gear would eliminate directional control problems and ground looping. By the way, when we talk of ground looping, this is not what we mean. For those of you who aren't familiar with a ground loop, it's actually the term used to describe an uncontrolled turn, or series of turns, by an airplane while in motion on the ground. And ground looping can be very violent. Engineers reasoned that with the advent of tricycle-geared aircraft, what with the center of gravity ahead of the main wheels and all, the airplane would tend to straighten itself out, and ground looping would become a thing of the past. But, surprise! Once again, the aeronautical wizards underestimated the ingenuity of the average pilot, who ably thwarts the laws of physics without even thinking about them. In an effort to keep you from falling into this ingenious category, let's take a look at some of the usual pitfalls and see how they can be avoided. The key to maintaining good directional control is to recognize and correct problems early. Stop that turn before it starts. Don't wait. One way to avoid loss of directional control is by understanding how the flight controls, elevator, ailerons, and rudder, really work. When landing an airplane with tricycle gear, keep the wheel or stick well back during the rollout to desensitize the nose wheel. Or, if you're flying a tail dragger, to put more weight on the tail wheel. You see, forward pressure, or insufficient back pressure, causes wheel barrowing, which puts more weight on the nose wheel. A heavy nose wheel makes the airplane become extra sensitive to rudder pedal movement, which can be aggravated in a crosswind when your inclination is to plant all three wheels firmly on the runway just as soon as possible. Landing this way only invites loss of directional control. On the other hand, if you relax back pressure, the use of a little more rudder than usual to correct a slight swerve could result in an overcorrection, and your airplane might suddenly dart across the runway, towards the runway lights, in a direction never intended and never imagined. And a word to the wise. Be especially careful when shooting touch and goes. Even when you think you've got everything under control, readjusting trim and flaps for takeoff may necessitate your leaning forward momentarily, inadvertently relaxing back pressure, and losing the airplane. If you get into a wheelbarrowing or loss of directional control situation, the best procedure is to close the throttle and smoothly but firmly pull the wheel or stick back to get the weight off the nose wheel, or onto the tail wheel, as the case may be. Now, another instigator of directional control problems are crosswinds, of course. When landing in a crosswind, remember that at touchdown, the longitudinal axis of the airplane must always be parallel to, and preferably over, the runway center line. The flight path of the airplane should also be parallel to the center line. Because if you touch down like this, or this, you'll probably lose directional control and could wind up back in the hangar a lot sooner than you thought. And side loads imposed on the landing gear don't do much for the airplane's resale value either.
4-1 Echo, wind check please.
Wind 270 at 13, gusting 20.
It's a good habit to double-check the winds on final. The pilot in command here knows that he must lower his left wing with left aileron and counter with right rudder to maintain the proper ground track at the moment of touchdown. A good pilot also keeps the capabilities of his aircraft in mind and avoids crosswinds which are greater than the demonstrated crosswind component. During the flight planning phase, he checks forecast winds at his destination and updates himself en route. If on arrival he discovers that the crosswind exceeds either the airplane's demonstrated capabilities or his own proficiency, he opts for the runway most aligned with the wind, or flies to another airport where such a runway exists. In some cases, the best decision might be to just stay on the ground until the winds die down. By the way, one of the most embarrassing kinds of directional control accidents occurs when the pilot tries to clear the runway by turning onto a taxiway before he's slowed down enough. Sometimes he's simply locked in to following that yellow line and forgets that he may be taxiing along at something very close to flying speed. That yellow line doesn't necessarily mean exit now. Too much speed on turnoff can result in an unscheduled cross-country. When you're slowing down, continue to follow the runway center line until you've slowed down enough to make that turnoff safely. Let's face it, there is really only one principal cause for almost every single directional control accident. It's that ugly little inescapable phrase called pilot error. Now, not knowing the basics is certainly one part of the pilot error equation, but there are also recent findings that show that preoccupation, too much stress, fatigue, or just plain being on a mental holiday can also put the pilot behind the airplane. Instead, why not use that sterile cockpit rule on yourself? Set aside all extraneous thoughts before you begin your approach, and don't allow your mind to wander. Think ahead of the airplane throughout the entire landing process. For example, anticipate drift, and continue to fly the airplane even after it's touched down. Additionally, inexperience, lack of recent proficiency, and especially lack of recent proficiency in a stressful situation can all result in the pilot getting behind his aircraft, or even freezing up at the controls. Remember the instruction on the mayonnaise jar. Keep cool, but do not freeze. Freezing or inadvertently panicking at the controls can also result in a pilot reverting to years of driving habits and trying to drive the airplane down the runway, even though deep in his heart, he knows that trying to drive an airplane with the control wheel has no effect. In summary, directional control accidents can be greatly reduced if, as pilots, we follow these simple rules. Maintain proficiency. Stay ahead of the airplane. Avoid wheelbarrowing by holding back pressure on the controls during rollout. Keep your flight path and longitudinal axis parallel to the runway centerline. Double-check your wind conditions on short final. Stay within the demonstrated crosswind capabilities, both yours and the airplane's. Slow the airplane down before taxiing clear. Keep your thoughts on the tasks at hand. And that's it for Part 1. We appreciate your attention. Be sure not to miss Part 2 of On Landings, when we'll discuss how to avoid accidents caused by landing long and by poorly executed go-arounds.